All right, thank you all, and welcome to the 2019 Walter Langbein Lecture and Awards presentation for the Hydrology section. My name is Scott Tyler. I'm the current section president, and I'd like to introduce the rest of the executive subcommittee of your section, the Hydrology section. Charlie Luce, secretary, is up here. Anna Barros is the president-elect, is here, and Jeff McDonald is the past president, and he is somewhere in the bright lights. I cannot see him, but he is here somewhere. So welcome all. All right, so just a few things to go through. We will be doing the awards to begin with, some of our section awards, and then the lecture will begin. The Langbein Lecture should begin at about 5 o'clock. So, and this will be a continuous operation as we go through. First off, this has been an amazing section meeting, an amazing AGU fall meeting, and that's because you all and we all have an amazing and wonderful fall meeting program committee. And that fall meeting program committee was headed up by Laura Bowling this year. I think she had somewhere of order 190 sessions to begin with to start sorting through. So far, it's been a wonderful meeting, at least from my perspective, and I think it has been from all of yours because no one has complained to me yet. So that is a wonderful thing. And again, so if you would, give me a round of applause for Laura and her committee. And most of us really, I don't think, understand how much work goes into that. It is an incredible amount of work, and I am looking for volunteers for next year. No. Well, I already have one. That's okay. All right, very good. In addition, let's see if this all works. So this is our schedule for this afternoon. We will have the Hydrologic Sciences Award. We'll then go through the Early Career Awards, and we have 3 this year, and we will for the foreseeable future. And then we will recognize our union awardees and our union fellows. And then we'll follow up with the citationist and the award of the Langbein Lecture for the last hour of the presentation of the afternoon. Very good. So first off, I just want to thank. We've already thanked Laura and her team. I want to thank all the volunteers that make this section run. So I would ask that if you are a committee member, one of our technical committee members, a nominator, a letter writer, an editor, what else are we? Section moderator, everything. If you have volunteered this year, stand up. Come on. I'm standing up, okay? All right, give yourselves a round of applause. And by the way, we are recording this, so I did see who did not stand up, and we do have committee assignments for next year. Seriously, I am looking for committees. Members, please come and see me. We need volunteers. All right, our first award is the Hydrologic Sciences Award. This was established in 1956. It's granted to for outstanding contributions to the science over a career with an emphasis on the last 5 years. Our award winner this year is William Kustas from the USDA, and I will ask Mark Parlange, who is his citationist, to come up and present the citation.
Okay, thanks, Scott. The first thing, it's truly a pleasure to present Bill Kustas for the Hydrologic Science Award of this year. I noticed this picture. I couldn't help noticing, well, first of all, our co-advisor, Wilfred Broussard, said I had to make a few jokes at Bill's expense at the beginning of this talk. And so one comes to mind. Bill used to work a lot in the wilds of Arizona, Oklahoma, and then suddenly in recent years I see it's always in vineyards, Bill. So that's not really a joke, it's the truth. Look, it's first of all, it's a pleasure to present my academic older brother. There were big shoes to fill. There was high expectations, and Wilfred was particularly fond of Bill as a student, and really enjoyed going into large-scale field experimentation with Bill. And they went to the Swiss Voralps to really do the first experiment for his PhD. Bill is extremely well known for advancing both the science and the application of remote sensing and the modeling of soil plant atmosphere dynamics to address hydrologic and climate problems. His sustained and original contributions in hydrology are highly appreciated by the international community. He has made important advances in the development of techniques based on atmospheric boundary layer similarity theory, momentum balance, heat and water vapor, conservation equations for computing surface fluxes of latent and sensible heat over complex terrain. He's been relentless in conceiving and designing and running large-scale multidisciplinary remote sensing field experiments that the community has benefited from, and has been a leader in a number of surface flux measurement networks for joint NASA and USDA studies. He's especially well known also for evaluating techniques, micrometeorological techniques, and has probably the thing that he's the most known for and that the community uses his work quite a bit is on developing physically based models to estimate soil and vegetation heat fluxes through remote sensing. So his approach really takes the application of remotely sensed surface temperature over variable surfaces, and then it includes a combination of microwave and optical remote sensing informations. And so they're now routinely used for mapping evaporation at basin and regional scales for continuous global scale evaporation. I also want to maybe finish on a personal point. Bill is a wonderful human being, and many young colleagues over the years have started their scientific career visiting Bill at the USDA, and many, I know a number of you out there in the audience had the pleasure while you were students at your universities, many European students, but of course many American students, Australians, and others that came and started their early careers. So Bill, we are really happy to be here with you today. This is really special, and we're all looking forward to celebrating with you this afternoon.
Thanks, Mark, for those kind words. I'm both honored and humbled to be selected to receive this year's Hydrological Sciences Award, especially given the class of past recipients. I would like to thank my nominator, Mark Parlange, and the supporting letter writers, including my mentor, Wilfred Broussard, Tom Jackson, who also received this award, and Gabby Catul, another receiver, as well as Yves Parlange and Andrea Ronaldo, as well as awards committee members for my selection. My 30-year research career after earning my PhD with Wilfred has been with the USDA Agricultural Research Service, and as Mark described, it's on both basic and applied research on evaporation modeling using remote sensing. Throughout my career, as Mark mentioned, I've been involved in both small and large-scale field experiments for modeling fluxes over a variety of land surfaces. I'm very thankful for the many ARS and university colleagues that have been involved in these experiments, and need to mention several who significantly contributed to my success and the success of these projects, and that includes Tom Jackson, John Pruger, Jerry Hatfield, Dave Goodrich, Steve Evett, Larry Hips, and John Norman. And in particular, I want to mention John Norman because I'm indebted to his collaboration as we reestablished the utility of land surface temperature applications for modeling ET. And I also need to acknowledge colleagues Martha Anderson, also from ARS, USDA, and Chris Hain at NASA for developing the multi-scale modeling system that's currently being used in estimating evapotranspiration at regional and global scales. This award also belongs to the many students and postdocs and visiting scientists that I've worked with, as well as support staff at the USDA Agricultural Research Service that I've had privilege working with throughout my career. And, you know, as a note with Wilfred, I remember in our field experiments in Switzerland that Wilfred had to go back to Cornell for about a month, and when he came back, he noticed I was drinking a coffee with schnapps. So I had both the positive and the sleeping aspect of that. And Wilfred was kind of concerned, but he got over it. Anyway, and I lastly like to thank my wife and family for their support, reminding me on what is truly important. Thank you.
All right, our next award fits the lower right-hand corner of all of these slides, which is Inspire the Future. And so these are our early career awards. And this year, as I said, and in the future, we will be awarding 3 early career awards through the hydrology section. The first award is going to Megan Konar from the University of Illinois. And the early career award celebrates and recognizes societal impacts by a scientist at his or her early career, in the first 10 years. So, if you will, Megan's citationist is Kelly Kaler, and Kelly, if you'll come up and say a few words.
Thanks, Scott. It's an honor to be here celebrating Megan's success. Megan Konar's scholarship has transformed our understanding of how economic and social forces influence global hydrologic flows, and it has clarified the effects of these dynamics on our most urgent water security challenges. Dr. Konar has distinguished herself as a scholar who is exceptionally creative in addressing compelling water resource questions in coupled natural human systems. Megan can move seemingly effortlessly between fundamental contributions to the field and more general synthesis and integrative work that resonates across academia and society. I believe that this ability to integrate disciplinary expertise and multidisciplinary impact is something that Megan does better than any other young hydrologist working today. At Princeton University, Megan's PhD research was the first to quantify the global virtual water trade network and to assess its temporal dynamics. She's continued to build on those efforts at the University of Illinois Urbana-Champaign, where she's addressing how climate change and trade policies combine to affect water use for the countries of the world. Most recently, she has shown that open trade leads to less water use for countries of the world on average. These efforts are notable not just for the breadth of their intellectual ambition, but also for the depth of rigor with which she addresses such complex, multidisciplinary topics. In every one of her research manuscripts, Dr. Konar asks insightful questions and adopts novel quantitative approaches to reveal the fundamental role that agricultural water use and food trade play in governing the vulnerability and resiliency of coupled water and food systems. She's conducting trailblazing work and successfully mentoring her students to push the boundaries of what it means to do interdisciplinary water resources science. In all respects, Dr. Konar's research trajectory has already established her as a world leader in the study of the water-food trade network nexus and her characterization of coupled natural human water resource systems. Her recognition today as a recipient of the 2019 Hydrologic Sciences Early Career Award is a richly deserved honor. Congratulations, Megan.
Don't be shy. Come on.
Wow. I am deeply honored to receive the Early Career Award in Hydrologic Sciences. I remember when I was a student in this audience, watching this award being presented, and I never dreamed I'd be up here receiving it myself. This award is particularly meaningful to me because my research is so interdisciplinary, but I've always felt welcomed and encouraged by this community, so thank you to all of you. First and foremost, I'd like to thank Kelly Kaler for his nomination and generous citation. He's been a role model to me since grad school, as well as a mentor, friend, and a constant source of inspiration. I would also like to thank Murugesu Sivaplin, or Siva. He has shown me the importance of developing a collaborative community and asking good questions. He has been a key mentor, friend, and advocate for me during my early faculty career. Additionally, I would like to thank Eric Wood, George Hornberger, Bridget Scanlon, and Arjen Hoekstra for their support throughout the nomination process and my early career. I would like to briefly take this time to honor Arjen Hoekstra, who unexpectedly passed away a few weeks ago. His work was a huge inspiration to me and to so many others. His tragic and untimely death has been really sad and is a huge loss to the scientific community. I was lucky to have an amazing cohort during my PhD at Princeton. I would not be where I am today without my grad school friends and mentors. Ignacio Rodriguez Iturbe was a wonderful advisor who pushed me to ask compelling questions and strive for elegant solutions. His passion for research is contagious and really inspired me. Andrea Rinaldo and Denise Mazeral were wonderful PhD committee members. Carol Dahlin and I were in the same group, and we've been close collaborators and friends ever since. I'm also deeply grateful to Tara Troy's amazing friendship and peer mentoring for more than a decade. Tara, I know we like to harass each other, but I'm so grateful for your sage advice, sarcastic humor, and having you to lean on. I would also like to acknowledge Rachata Munapirakul, Brian Ellis, Dan Wright, Steve Good, Matt Reed, Francis O'Donnell, Jason Todd, Caillou Guan, Enrico Bertuzzo, Trenton Franz, and Justin Sheffield, and many others for their friendship and guidance during my PhD. I'm especially indebted to my amazing students and collaborators with whom I, of course, share this award. Many of my students are here today to celebrate with me: Landon Marston, Nicole Jackson, Paul Roos, Denise Burfin-Karakok, and Junren Wing. Thank you for your hard work and creativity. My colleagues in civil and environmental engineering at Illinois have been wonderful to work with. I have benefited from camaraderie and weekly lunches with all of them: Jimin Kai, Marcelo Garcia, Praveen Kumar, Gary Parker, Art Schmidt, Ashton Stillwell, Rafael Tinoco, and Al Valaki. Finally, I would like to thank my family. My parents, Pam and Tom, always encouraged me to do what I love. I had 2 children as an assistant professor, and I'm grateful for the family-friendly atmosphere and supportive policies at Illinois. My daughter Sarah is 6 and Sam is 3, and they both constantly are entertaining and ensure that there is balance in my life. And then finally, Russ Arani, my husband, has been instrumental to everything and has made it all a fantastically fun journey. So, thank you.
Very good, thank you. Our next Early Career Award winner is D. Long from Chengdu University, and I will call up his citationist, Siva Sivapalan, to give the citation.
Okay, it feels great to be at the podium giving this citation, but I feel I'm in a strange situation in that I know D. Long's work more than I know him personally. I met him finally just a few minutes ago. Dr. Long is receiving this Early Career Award for pioneering work aimed at monitoring space-time dynamics of water balance using remote sensing. His early work focused on evaporation estimation using thermal infrared remote sensing. He developed parameterization schemes of energy balance for dry and wet limits of soil moisture through interpretations of relationships among land surface temperature, vegetation cover, and soil moisture, thus helping to improve earlier generation of models of spatial evapotranspiration. He later expanded his research to estimation of large-scale changes in groundwater storage using data from gravimetric satellites such as GRACE, and to improving the spatial resolution and reliability of water storage changes. Back in China, he developed algorithms to retrieve precipitation, river water levels, and discharge, as well as soil moisture in the Tibetan Plateau. These have led to major improvements in understanding of hydrological processes over alpine regions. Now, rapid development of satellite remote sensing in recent times provides an unprecedented opportunity to capture spatio-temporal variability of atmospheric and land surface processes and to address scientific questions related to predictions in ungauged places. Dr. Long is well positioned at the cutting edge of this exciting area and is well poised to combine hydrological modeling and remote sensing at large scale to address such questions. Dr. Long's outstanding contributions to research, mentoring of students, leadership, and service merit his receiving the Hydrological Sciences Early Career Award. Congratulations, D. Long.
Thank you. And I'm so honored and delighted to receive the AGU Hydrology Section Early Career Award. And first and foremost, I'm grateful to Professor Sylvia Palin for your generous nomination, the AGU Hydrology Section, the Honors Committee, and my advisors, Professor Vijay Singh from Texas A&M University, and Bridget Scanlon from UT Austin, and as well as Martin Clark for their candid support. And I very much appreciate all of the people who helped me with my career. And I was very much inspired by the groundbreaking work of many pioneers who have advanced the field of remote sensing in hydrology. And I have been keenly interested in remote sensing and hydrology, especially on thermal infrared remote sensing based evapotranspiration estimation since my study at Texas A&M University. And following that, I very much enjoyed working with Bridget Scanlon and Laurent Lanvert at UT Austin, where they generously helped me to expand my expertise to include gravity satellites and land surface modeling. And since then, my vision of remote sensing in hydrology has been broadened by looking at water storage chains from many different angles. And this has helped me to understand the strengths and the limitations of many different approaches and to try to capitalize on the distinct advantages of each. It's my privilege to work with many passionate students and colleagues at Tsinghua University on the hydrology of the Tibetan Plateau, which largely determines the freshwater availability for many downstream Asian countries. The combination of remote sensing, ground-based monitoring, and modeling has large potential for improving our understanding of hydrological processes at various spatial temporal scales under a changing environment, which should help to mitigate climate change impact on society. And as ever more satellites are launched and cutting-edge observation technology developed, hydrology should explore data analytics and artificial intelligence to continue our rapid progress into the future. Last but not least, I'm indebted to my parents, my wife, and my son for their strong support and enduring love. Thank you very much. Thank you.
Our next Early Career Award goes to Kaveh Madani, and he will be introduced by his citationist, Balaji Balaji, I'm sorry, Rajagopalan.
Thanks, Scott. It's phonetic, so like most all Indian names are. So, Good afternoon, everyone. Welcome. It's my pleasure and honor to provide the citation for Kaveh Madani. Madani is without doubt among one of the most productive, well-cited, and active members of our community at the interface of water, environment management, science, policy, and society. He's also one of the few scientists in the AGU community who served with courage as a high-level environmental decision maker at the national and international levels, particularly the Deputy Minister of Environment in Iran and the Vice President of the United Nations Environment Assembly Bureau. After the former assignment and all the exciting stories I'm sure all of us and all of you read in the New York Times stuff of movies, I was talking to Kaveh a little while ago, and he said his life is suddenly very quiet. So it is that intellectual curiosity and restlessness that sets him apart among all of us. Kaveh receives this award for his fundamental contributions to integrating game theory and decision analysis methods into conventional water resources systems models. His proven dedication to education, outreach, raising public awareness on environmental and climate issues, and selfless service to hydrologic sciences community has had major societal impacts and continues to have. For all his contributions, the Hydrologic Sciences Early Career Award is a richly deserved recognition. Congratulations, Kaveh.
Thank you so much. Thank you, Balaji, for such a generous citation and for leading this nomination. Thank you, Amir Kuchak, Greg Chiraklis, Pete Laux, and Jay Lund for endorsing this nomination. It's great to have good friends. I'm nothing close to a traditional hydrologist, and I still struggle publishing my papers in water resource journals because I talk too much about humans. So it's really rewarding to get this award from the hydrologic section and the AGU. I'm really thankful. And thank you to my mentors, mentees, and colleagues who I share this honor with. Special thanks goes to my mentors, Keith Heipel, who got me into game theory at the first place, Jay Lund, my PhD advisor, who gave me the courage to take courses in economics, law, and political science out of my comfort zone, and always he wanted me to develop my own signature area. My postdoc advisor, Ariel Dinar, an economist who helped me be a better communicator. And to my students and postdocs who helped me satisfy my curiosity in exploring new areas of research, from whom I've learned a lot. I have a lot of friends. I'm lucky to have a lot of friends and good colleagues around the world. I thank them for their support and friendship. I can't name them all here. I apologize for two reasons. One is because luckily there are too many. And second, after all happened to me in politics, I don't know if naming them is the right decision. They can get into trouble later on for being associated with me. One of them has been threatening me that if I don't mention his name here, he would end his friendship with me, Ali Alaipur, so I mentioned him here, but the rest I'm sure you're more mature and will forgive me for not doing that. But your presence in my life has made a big difference. Thank you for being there. And last but not least, my parents, and my beautiful wife, who have not given me anything but love, and even though I've made their life miserable many times because of my choices. Thank you.
thank you very much. Let's give a round of applause to Bill, Kaveh, Dee, and Megan. Congratulations. That'd be great. Thank you. And also thanks to Balaji Rajagopalan. I did get it. I knew it. Very good. All right. Our next very fun job is to celebrate our union awardees and our fellows. So at the union level, tomorrow these individuals will be recognized at, I believe at 6 p.m. at the union medal ceremony. So I do encourage all of you to go. It's a wonderful event, and celebrate your colleagues. And I'll ask as we'll go through these, and then I'll ask at the end for a round of applause. So first, our hydrology section fellows. It was a wonderful fellows collection this year. Barbara Beacons, Jamin Kai, Reed Maxwell, Tom Painter, Beth Parker, Carl Stiefel, and Chung Mao Zhang. Congratulations. Let's do this now. Will you stand if you're here, and let's give them a round of applause. Congratulations. It's being challenging. Okay. Our next is the Robert Horton Medal. This is the top union award in hydrologic sciences, and this year's award winner is Majid Hassanizadeh. And Majid, if you are in the audience, would you rise and be recognized? He's in the back there. Congratulations. Let's try this. There we go. That's better. And then we also had several other awards. We have a McElwain medalist this year. It's a pleasure. Amir Agakuchak, and also an ambassador award for Constance Millar, and Connie is a joint member of the hydrology section and I believe global environmental change. So let's give them, are they here? Is Amir here? There he is. Let's give a round of applause. Congratulations. Okay, just a couple of quick announcements before we get on to the lecture today. I just want to remind you the Paul Witherspoon lecture is on Thursday at 1:40 to 2:40, Moscone 2022, and the lecture this year is going to be given by Patrick Reed, Conflict Coordination and Control in Water Resource Systems, Confronting Change. And we've seen all day, the last 2 days, issues of change, climate change, political change, and their impacts on water. So I think that will be a wonderful seminar. I do encourage you to be there for that. A couple other things, announcements. The AGU, our hydrology section business meeting and reception, mostly reception. We'll try to keep the business relatively short because I know you're standing and it's been a long day. That will be tonight at 6:30 to 8 at the Marriott Marquis. It is a ticketed event, so I hope you have your tickets. If you don't, there's no AGU people in the room, I don't think. I have noticed that you can sneak in if you have to. So I would, you didn't hear that from me. And again, that's sponsored by your section, but it's also co-sponsored by COASI, the Consortium of Universities for the Advancement of Hydrologic Sciences. So we appreciate their support. We're getting on to our lecture, but before we do that, you've all been sitting for a while, and I recommend, if it were me, I would want to stand up and shake a little bit before the lecture. So if anybody wants to stand up, you all should stand up. Get a little, loosen up, okay? Very good, very good. Now, turn to your left or right, if you don't know the person to your left and right, and introduce yourself. Say who you are. Very good. Hi. Okay. Okay, that's enough. That's enough. Very good. Even the Langbein Lecture won't sit down. That's, please, okay, very good. Thank you. So, it is my, it's the last time I do that, I guess. I don't know. It is my pleasure to announce the Langbein Lecture Award winner is my friend and colleague, Effie Fafula Georgia. The Langbein Lecture is given for a lifetime contribution to the science of hydrology. and I would say in this case, and unselfish cooperation in hydrologic research. It is a pleasure to be able to listen to Effie's talk today. It will be on, sorry, I can't read without my glasses, but she will tell us what it is. I would like to call up on the stage her citationist, Vitek Krajewski, who will give the citation.
Thank you, Scott. It is my privilege to be here and to present Effie to you before her Langbein Lecture. I first met Effie in early 80s. It was at an AGU meeting, I think in Baltimore. She was giving a talk, and somebody sitting next to me, I can't remember now who, probably Jim Smith, whispered to me, "Here is the next star in hydrology." It really happened that way. I met Effie again in Caracas. Ignacio Rodriguez Iturbe and Vijay Gupta organized the first international precipitation conference, there at the outskirts of Caracas. And one thing that I remember very well there was going jogging, actually running with Effie and a couple of other people. And so I was younger, in shape, and I remember, running and looking over my shoulder and thinking, like, when will she slow down? So that I could slow down. She never did. She kept running and running and running, and she is still running strong, today. Effie has made many contributions to hydrology and geomorphology, and too many for me to recite them, here. She will tell us all in her lecture which she considers the most important. Working on that nomination was her nomination was a collective effort on behalf of all of us. I got more support letters than allowed to submit, but I can tell you that contributions included input from Dennis Lettenmeyer, from Surush Surushian, from Chris Kumerov, from Praveen Kumar, and from Ardeshir and at the Bash. Langbein Lecture is also for unselfish cooperation in research, and Effie is a primary example here how to do it. She has been involved in many committees and panels, many organizations. Again, too many to list, here, always representing us, representing hydrology, often always advocating for hydrology, often fighting for hydrology. And for this, we thank her. So thank you, Effie, for your contributions. Thank you for your leadership. Thank you for your friendship. And thank you for being one of us. Thank you.
So, thank you, Vitek. You brought up fond memories from the early 80s. In 1959, Walter Langbein was at the peak of his career, leading the nation in hydrologic sciences. He was also the president of the hydrology section of AGU. In the same year, a 2-year-old was playing happily in a remote village in Greece. Little did she know that one day would have the privilege and honor to be in this podium and pay tribute to that great scientist. Many people have contributed to and have enriched my career. Some of them have guided my career, and I'm very thankful to them. There are too many to mention here by name. Many of them are in this room today. Thank you. My students and postdocs have always been a source of inspiration. We stretch each other and we grow together. Thank you. But today, for the first time publicly, I want to thank my parents, my late parents. They taught me the values of knowledge, discipline, and integrity. They also taught me very early on not to respect authority for the sake of authority, but only if authority had proven itself with the same values of knowledge, discipline, and integrity. So today, I want to dedicate proudly this award to them. Unfortunately, they passed too early, and they didn't have the chance to see that I did something useful with the values they instilled in me. And I have been true to those values. So I proudly dedicate this award to their memory. Thank you. So when the awards were announced in late summer, I received an email from my friend, Bill Dietrich, asking me whether I had a copy of the picture of the fit and length of water Langbein. Thank you, Bill, if you are in this room, for sharing this picture, because it is a very telling picture of one side of Langbein, that of a keen observer of nature. Is this screen showing opposite? Yeah. But I'm very familiar with another side of water Langbein, that of a theoretician. I remember early on as a graduate student reading voraciously all these amazing papers, the professional papers of USGS that were coming out at that time. This is a few of them with Luna Leopold and with Rediger, where they were introducing concepts of thermodynamics, minimum variance, stochastic elements such as random walk to understand landscapes and rivers. There is another side of him, of course, the practitioner, always with an eye on bringing together the theory and practice. Let's not forget that he was a civil engineer. His first job before he joined USGS was in a construction company, where he was given the task to control the groundwater pumping for the subway excavation in New York. This is a wonderful paper of EOS transactions of AGU at that time, where he evokes mathematics and a nice asymptotic formula to relate the return period of floods from the partial duration series and the maximum annual flood series. This was very important in the absence of data at that time. Water Langbein, the science communicator, it's worth having a read of the priming of water, where he was using budgetary monetary budgets to explain the water budget, blood vessels and circulatory systems and so forth. It's a nice reading. Water Langbein, the visionary. I mean, he, together with many others at that time, they created the US Geological Survey water program. They developed from scratch mostly the national network of hydrologic data, which instigated the flood insurance program. He was very much involved in the International Hydrologic Decade, was sponsored by UNESCO. He was very much involved in the International Association of Hydrologic Sciences, where he created and chaired the first committee on mathematical modeling, and was involved with WMO. One more thing that I would like to point here is that he was visionary and also cautioning against, in times of budgetary constraints, invest in our budgets only to collect data and not invest in the science to analyze and learn from this data. So in this wonderful Water Facts for the Nation volume, He quotes Henry Poincaré and says, "Science is built up with facts, as a house is built with stones. But a collection of facts is no more a science than a heap of stones is a house." So when I was president of the hydrology section of AGU, obsessed with the history, always believing that we have to look at the past to move forward, I created what was called the Virtual Hydrologist Project. For the people young in the room, please go and visit it. We collected papers from several of the luminaries in hydrology. For example, for Walter Langbein, there are more than 50 of his papers posted as PDF files. It's a long and hard work that we did at that time. It's hidden somewhere in the website, so you have to search for it. So, saying all these things about Walter Langbein makes me feel very small, which I am. And I would like to take the opportunity today to present a few things that I have done in the past 35 in my life. I think I've worked on too many topics, probably too many, that I would not advise any young person in the room to spread so thin, but I did. One is precipitation estimation and prediction. The other is networks, both tributary and distributary, meandering and bedded rivers, and for the past several years in intensively managed agricultural landscapes. The driving scientific questions, if I am to summarize them, have always been: how do physics organize precipitation systems at different scales in space and time? How can I take advantage of this organization to improve prediction, modeling, and estimation, as I will talk today? Can we gain mechanistic understanding from the beautiful landforms and landscape patterns that we see around us? And finally, how do perturbations propagate through a complex system, and how do they determine its vulnerability to change? Our data have been multi-sensor observations, starting years ago with rain gauge data, the zerometer data from the University of Iowa, 2-minute temporal rainfall data to understand the intermittency, NEXRAD data, later the TRIM, the Tropical Rainfall Measuring Mission, and later the Global Precipitation Measuring Mission for precipitation. And then for landscapes, we worked a lot with LiDAR data when they first started becoming available, and with Landsat. I was also happy to be at the University of Minnesota St. Anthony Falls Laboratory, and we did a lot of experiments. My students Arvind Singh, Vamsi Gandhi, and Viktor Sapoznikov on landscape evolution. We did a lot of work in river morphology and bed forms and river deltas. My research over the years has spanned a large range of scales, from what I call the pebble scales, how do tracers move in a river and form the bed forms, plot scale, single meandering scale, watershed scale, continental scale, like large basins that are emptied by river deltas, and global scale. Behind all this data, there is a lot of science to extract useful information. And very quickly, I want to mention some. My former student, Paola Pasalacual, for her PhD thesis, developed a beautiful methodology to take LiDAR data and convert them to river networks. And that was, at that time, a very sophisticated methodology that uses nonlinear diffusion and geodesic paths that are informed by energy minimization on the rivers to develop this algorithm. Later, we mined Landsat data because, of course, meandering rivers move very quickly. So we had to look at 30 years or more of Landsat data and understand several questions. For example, if I freeze this picture and you see only one meander bed, can this tell you anything about its life until that time? What brought it there, and how will it evolve? We know that there are nonlinearities behind the hydrodynamics, sediment dynamics, but do this impair themselves in the landform geometry? And how do upstream and downstream propagate? So if I have a cutoff, for example, how do I see it, and how far upstream and downstream do I see it in lateral migration of rivers? These are very important questions, not only theoretically, but practically. Finally, in river deltas, although we have a lot of work in hydrology and hydrogeomorphology, Andrea Rinaldo, Ignacio Rodriguez Iturbe, in tributary basins, fractal river networks, and so forth, no work was available in characterizing river deltas. This is a simple river delta that I have here, the Walks Lake Delta, but if you see, and I'm sure you have seen a lot, there are beautiful topologies that are formed by these distributary systems that are complex. They have a lot of splitting and rejoining of channels, and we developed the theory with my former postdocs, Alejandro Tejedor, on using directed graph theory for not only quantitatively describing the delta river networks, but also ask questions such as, can I tell anything about the physics behind them? Can I come up with the topological scheme that can tell me this is different from the other? And finally, very recently, we, following on Langbein steps, actually, we proposed an optimality principle. That is, if deltas are left alone, there is an entropy behind it, not the typical entropy, but something we introduced, which is the entropy rate, non-local, from the apex to the shoreline, that they try to optimize such that they maximize their diversity of sediment and water delivery to build land and maintain it. And of course, river deltas, it's not only that water and other things go through the channels, they go through the islands, it's a whole system, and we develop a theory of coupled networks. Too many things. The last thing that I would say from previous work is I spent at least 6 years or 7 at the Minnesota River Basin, where really both climatic change and intensively managed agriculture, especially you see in the graph there, the intensification of soybeans has changed the system in its hydrology and has cascaded down to a lot of sediment in the rivers, a lot of nutrients, nitrogen, and legacy phosphorus. But today, I want to talk about a topic that has been in my research portfolio forever, is rainfall, and 2 specific topics: global precipitation estimation from space and seasonal prediction. Walter Langbein, in his report there, you see in the bottom graph that during his time, the number of rain gauges went incredibly. The steep slope there is in the 60s, where we ended up with around 12,000 rain gauges in the United States. He mentioned somewhere something, again, very visionary, that precipitation stations are put where people live, and not where precipitation is more variable and therefore more important to record. And we suffer from this even today. We don't know how much snowfall is in Sierra Nevada and other places. So how many rain gauges do we have that cover Earth? Because now we don't care about the US only, we care about the whole system, understanding how interconnected it is. This is a nice kind of movie from NASA, where basically you can see that if you put together all the rain gauges, they're just going to concentrate into basketball courses. Not very much. To understand the things that we care about, the global energy and water balance, to do hydrologic prediction in basins that we don't have in situ measurements, to validate climate models and detect changes and trends. So how do we measure precipitation from space? We have the geostationary infrared constellation of satellites. They sit very much in altitudes of 40,000 kilometers, and they look down on Earth. The advantage of them is that we can have one observation every 15 to 30 minutes, every point on Earth, but what they see is the top of the cloud. Not much information, although advances have been made in translating that to precipitation. We have the low orbiting satellites in microwave. That is a constellation of around 13 satellites now. They get more information. They just get the emissivity from the ground that goes through the cloud. Whatever is in the cloud changes that emissivity. And depending on the frequency channels, the 13 channels here for the core global precipitation mission satellites, converts this to what we call a microwave signature. For example, here you see the brightness temperature. That's the temperature of a black body that will have the same radiance at the same wavelength. So instead of one value at the top of a cloud, I have a 13-dimensional vector of brightness temperature. Now, how can I convert this brightness temperature to what really was on the cloud and how much precipitation I'll have near the surface? That's an inverse problem. Now, what saves us is that the core, only one of the satellites, of the 13 satellites, is the only one that has a radar active sensor in space, which basically has two frequencies, Ka and Ku. They have a small swath, the Ka 125 kilometers and so forth, the Ku 250, and the microwave sensor has much more broader swath, 885 kilometers. So what we try to do is leverage this coincidental data and learn from the active sensor by comparing it with the passive sensor what precipitation was. You can make the analogy that basically the radar does a CAT scan and the microwave does an X-ray. So the NASA operational algorithm, and this is courtesy of Chris Kummerow, who has developed and really maintains the operational algorithm of NASA, relies on forming databases of possible rain structures and microwave signatures and doing a Bayesian inversion and coming up with precipitation. But if you ask the question, how accurate are these retrievals globally? The classical approach is to do scatter plot analysis, and we see a lot of this in the literature, pixel-to-pixel comparisons. Now, if I give you these two fields, which are in 1 kilometer resolution, the right one is the same exactly sifted by 7 kilometers. Guess what would the scatter plot give me? Well, it will give me that, R squared 0.54. This is fine, but me as hydrologist, I would prefer if I got a little more information and you told me that, look, you don't resolve precipitation at 1 kilometer, but in 10 kilometers, then by 10 kilometers, we're fine to put it in a hydrologic model. So we, with my postdoc, Clement Guillotot, we proposed recently a concept of effective resolution, which is the finest scale at which retrievers accurately reproduce the local spatial variability of a reference product. So the framework behind is a little complicated mathematically, it's done in wavelet space, but I would like to walk you on the concept because it's very simple. Suppose I give you a field at 10 by 10 kilometer resolution, which is to the right here. This is a box of 10 by 10 degrees and a precipitation field at a resolution of 10 by 10 kilometer. Now I can use a filter and upscale or smooth or average this field and go to 20 kilometer, 40 kilometer, 80, 100 kilometers, say dyadic resolution. As I lower the resolution of that field, of course, I lose information, but I can keep this information if my filtering is done in a, say, orthogonal wavelet decomposition in which I can keep at every scale the information that I lost. Now, as I smooth and smooth, my variance goes down, and this is expected, of course. Now, if I sit at the low resolution field, in this case, the 160 by 160 kilometer resolution, and I ask the question, you have kept the details that you lost, and you can add them back, but how much of this detail is real signal, structural variability, versus it is noise? Well, for that, I would need a reference field, and here would be my precipitation radar field, which I can compare and build what I would call the variance that is explained by the precipitation signal, meaning the structure, the patterns that exist, and the rest is noise. And then I can start marching along the scales here and say that if I started from 160 kilometer resolution and I added the fluctuations that I removed and I go to the next scale, how much of this variance is signal and how much noise? And I can do that, so in this case, a lot of that is precipitation signal, lesser noise, and I can do that in all my scales. And when the noise becomes more than the signal, I can safely say that the scales less than that are not resolved. So this we call the effective resolution. So let us look at the state-of-the-art precipitation products as produced by NASA and so forth with the algorithm and see what is the effective resolution. This is done out, as you can see there, 16,000 orbits, which is a lot. And the areas that you find white here is we didn't have at least 150 overpasses to do statistical analysis. So you see that over ice, of course, I do very bad, as expected. Over mountains, I do bad. But we also see that there are some areas that we do bad, meaning effective resolution 80 kilometer, meaning although the footprint of the sensor is 5 or 10 by 10 kilometer, we cannot resolve the variability in anything less than 80 by 80 kilometer. Over the ocean, by the way, we do not bad, 10 to 20 kilometers, missing some of the tropics. Now, we know that this is a very highly underdetermined problem. If I look in this database and I point out or pick up one of these, I call them atoms in that 13-dimensional radiometric space, and I look at the atom next to that, meaning another point in that 13-dimensional brightness temperature space that has the same exactly signature. Now, this happened to be two orbits, one in the Atlantic, one in the Pacific. If I look at their precipitation, I see that the one has 4 millimeters per hour, the other 76 millimeters per hour. No wonder, and that's something we know, we underestimate the extremes. Now, I could look at other things like 2 meter surface temperature and all of these things. They don't help, take my word for that. Now, is it coincidence that we found these 2 points? No. Because if you look in the whole database, here we look at 4,000 neighbors, we see, and we do a variogram, all of you are familiar with variogram, we see the horizontal axis is a distance in the radiometric space, Euclidean distance, and the vertical is the variance of the surface rain. That variogram tells us that even if we push the limit of radiometric distance to 0, we don't push the variance of the surface rain to 0. In fact, we have a lot of unresolved variance, standard deviation of the order of the rainfall intensity itself. That tells us 2 conclusions. The one is that increasing the size of the database will not do it. We have millions of atoms in that database. We can improve our inversion algorithm. Instead of Bayesian, use some others that we had explored in my group with regularization and so forth, but the accuracy will be very limited. So what we propose is to look at the patterns, and this is something that I put in the title. That is, if I concentrate in these 2 pixels, which I have in circles there, I see that the brightness temperature at 37 gigahertz, one of the frequencies here, the one is embedded in a brightness temperature around that is much higher. That is, it's a local depression, which is an indicator of deep convection. I have a lot of ice high up in the clouds, up to, say, 10 kilometers, which has created a deep depression locally in that radiometric signature, but if I look at the surroundings, it's very clear it's a deep depression system, as opposed to the other one, which is at the edge of the system, shallow convection. No wonder the one had 76 millimeters per hour, and the other had 4, as known from the radar that knows more the truth. So, of course, I could put, instead of 1 pixel in my database, 10 of them. But imagine if I do that, I increase the dimensionality from 13 to 130. It's impossible to do an inversion there, Bayesian inversion. So the problem becomes how to extract the most informative non-local parameters, meaning they will tell me about the neighborhood from the brightness temperature patterns, and how to increase identifiability and reduce the retrieval uncertainty. We propose to use convolution filters, of course, because the depression, I can extract from a second derivative convolution filter. I can use an averaging, say Gaussian, to tell you that I am in high brightness temperature in the vicinity, or I can use a gradient filter. And I don't have time to go into that, where would be the most informed filter to use. But at the end of the day, we would have here the field, this is at 89 vertical gigahertz, convolved with, say here is a derivative filter in the along track direction, and I would assign to every pixel another parameter, which is non-local. It will be basically an additional feature in that pixel that I try to resolve that will tell me what happens in its neighborhood. Now, we implemented that within the database that is an operational algorithm, and I want to show you some results. For example, from almost 1 million profile database, if I look in the vertical, this is the mean absolute error in the retrieval. The horizontal is how many atoms I combined in the neighborhood. So if I want to retrieve here, how many from the surrounding atoms in the radiometric space that I use. If I use around 10, I don't improve. But the thing is that if we add only 3 non-local parameters, in this case happen to be 37 and 89 gigahertz derivatives and 1 average filter along the direction of the sensor, you see that we reduce the mean absolute error by 11%. That's a significant overland. That's a significant reduction, and of course, we do better in estimating extremes. If I look at the rainfall miss rates, we know how important it is to identify whether there is rain somewhere in the ocean or there is no rain. And usually, the algorithm now underestimates the extreme rainfalls and overestimates the very low rain. It tells you that there is more rain or there is rain where in fact it is not. So we reduce the miss rate by 25% and the ocean rate by 20%. Many more results that I can present, but there's a lot of potential just with this simple acknowledgement that every pixel is not an independent realization of an ensemble. It has to know what its neighbors are doing. So what's next? Is machine learning the solution? We have millions and millions of pixels to do learning from. What I want to say here is eventually maybe, but not without physically based dimensionality reduction first. We have to understand what we're doing before we input all our data in a machine, input, output. We have to train convolutional neural networks because after all the operations we did to learn were convolution, so convolutional neural networks would be the place to really to go. And through what's developed now in the literature, the backpropagation methods learn what patterns did the neural networks learn to tell me the right precipitation rate. We could all work on specific storm systems. We're not doing at all well in snowstorms and learn what do we have to learn to improve the estimation and detection of snow. Finally, something I didn't talk about. I talked about the infrared. I didn't spend time. The microwave sensors, which are very important. But after all, you cannot have only one point seen every 3 hours or several hours. We have to combine all the measurements that we have, and NASA is doing that through the new product, which is called iMerge. Now, if you try to mix products, you better know what uncertainty each one has. So we're working on defining the effective resolution, not only in space, in time also, because that will be dynamic evolution of each of the products because before you throw them into merging a product of NASA. A lot, and I could stop here, but I will not. The second problem is seasonal prediction. So I spent 30 years at the University of Minnesota, and I have been for 3 years at the University of California, Irvine. I moved from Minneapolis, which had 32 inches of rain, 53 inches of snow, 112 precipitation days, in average temperature in January, 7 degrees Fahrenheit. And I moved to Irvine, where I have 12 inches of rain, 0 inches of snow, only 36 days of precipitation, and average temperature in January, 46 degrees. I cannot complain. Our precipitation in Minnesota was really during the spring and the summer, and our precipitation in Irvine is during the winter months. If you want more, you can see here that it's kind of boring in the Midwest because the coefficient of variation of the annual series, interannual variability, is very small. The coefficient of variation is of the order of 0.2, standard deviation over the mean. Now move to California, in South California, what do you see? A coefficient of variation of around 0.6, 0.7. That's a lot of interannual variability. I mean, the standard deviation is of the order of the mean. Even more, half of our annual precipitation falls in only 5 to 10 days, atmospheric rivers and so on. So what controls the precipitation in Southwest US? It all comes down to pressure. We know that we have high and low pressure systems that are formed in the Gulf of Alaska, which affect the jet stream from its average condition, driving it to the north or to the south. These pressure patterns are usually associated with ENSO. You see the typical La Niña and typical El Niño event. The physics behind this is well known. This is a schematic from Kevin Dertberg, 1998, because these pressure systems develop Rossby waves, which have alternating cyclonic and anticyclonic patterns and affect jet stream. So ENSO, all of us know, is the go-to mechanism for predicting precipitation. Now, if I ask Jeff Dozier, my friend Jeff, I don't know if he's here, he always keeps telling me the joke. My friends ask me, oh, it's an El Nino year, will it be wet or dry? And I tell them, yes. So if we look, blue is the precipitation in November to March, the winter precipitation, which is most really of the annual precipitation, and the red is the Nino 3.4 index. We see that we have a lot of dry misses, meaning we had dry, although El Nino conditions told us otherwise, we have some wet misses. If we look after 1980, we see again wet misses, dry misses. We see more. We see false wells, wet alarm, meaning some very high El Nino, significant. And this is standardized anomaly, so one would mean one standard deviation above the mean. And a lot of false alarm rates. Some of them is the well-known El Nino Gonjila in 15, 16, which was a dry year, the strong La Nina in 2010-11, which was a wet year, and the ENSO neutral in 92-93, which was one of the wettest years of the year. The multi-year drought, and of course the inability of ENSO to capture precipitation events in the last year has produced a lot of work paying attention to what I would say increasing importance of the Western Pacific. Now, I just, of course, you cannot see these papers there, but I will also give you a few of quotes of some of them. For example, here this paper cautions us against ascribing various extratropical anomalies in the Pacific Northwest to ENSO, a go-to mechanism. Heating anomalies that do not depend on ENSO may excite extratropical responses that include extreme west coast ridges. A cross-Pacific pathway of Rossby waves is propagating from the western subtropical Pacific towards the Gulf of Alaska, and so forth. In a recent paper in my group, led by my student Antonis Mamalakis, and with atmospheric physicists and climate physicists at the University of California, Irvine, we proposed a new Western Pacific pathway, we called it. It is composed of 3 mechanistic steps. The first one is an atmospheric bridge, which basically takes anomalies from the southwestern Pacific, close to New Zealand, propagate them through an atmospheric bridge to the north, creating anomalies there. The second part of the mechanism is local Earth-seek coupling, maintains these anomalies, and the third part is that we have Rossby waves followed in a different way than the El Nino and deflects the jet stream. The second step and the third step are known. What was not known, and a little controversial, is this atmospheric intercontinental atmospheric bridge. Interhemispheric atmospheric bridge. So the hypothesis we put forward is that if we look at close to New Zealand, we define the New Zealand index is of the same area as the Nino 3.4, 30 by 15. The anomalies there, warm or cold, modulate the southern Hadley cell, which at that time, at the late boreal summer, is expanded and reaches up to the Philippines. And depending on what anomalies we have, cool anomaly in the New Zealand index, it strengthens the southern Hadley cell, or warm anomalies weakens it. Now, we wanted to test this hypothesis. There are many ways of testing it. We did the physical variables that would tell us whether we have the strengthening and weakening of the Hadley cell. For example, if we take the warm minus cool NZI years, we expect weakened convection in the northern hemisphere, which we see. And we also expect increasing incoming solar radiation in the northern hemisphere, which we see. We also check other variables like meridional winds, etc., to test the hypothesis of this interhemispheric bridge during the boreal summit. Someone can say, well, could ENSO be behind it anyway? And I put here the provocative title, is this Western Pacific pathway independent of ENSO? Of course, I put it in quotes. Nothing is independent of anything else. But the right question is is there information in the Western Pacific pathway and these anomalies that cannot be explained by ENSO alone, and add information content for prediction? Too much to go here, but if we do the Gangier causality, which is conditional correlation here, and you condition on ENSO, you see that 2 months later, for example, and I cannot show there, we see the anomaly, this is standardized anomalies, propagating from the south part of the Western Hemisphere to the north, and then 4 months later, they are maintained in the Northern Hemisphere. So we cannot reject the hypothesis of ENSO been explaining all this propagation of the anomalies from the south to the north Western Hemisphere. Has this Western Pacific pathway amplified over the past 4 decades? As I showed you, we have many more hits and misses and so forth. So based on observations, we looked at the New Zealand index and its correlation with the anomaly that introduces close to the Philippines. We called it the Philippines index. And we looked at it during the periods that we have this atmospheric bridge, and during the periods that we expect to see the Earth-sea coupling. You see that the correlation is significant. The hypothesis cannot be rejected, where it is interesting that the observations for the same exactly analysis before the 1980 points out that there was no significant correlation. Now, someone can say, well, that's just one realization. Could that be internal variability and would change in the next years? Could be external forcing, or could be simply data quality. Before 1950, we didn't have that much data. We tested this hypothesis by using the CSM model and the 40 ensemble members. And we basically look at the same analysis for the 40 ensemble members. And here you see at the top from 75 up to 2005, where the members of the ensemble go. We have the correlation of NZI with EPH, and also the standard deviation of the ensembles. Now, if we do that for the before 1960 period, you see something significant, that after 1975, the ensemble mean correlation is increased, and also the ensembles converge. That cannot be chance. We have 40 ensemble members that are basically same physics but different initial conditions. They don't communicate with others to converge. So this convergence further builds confidence in the hypothesis that there is a change that has happened after 1970s and so forth, which is most likely attributed to forcing and not internal variability. So we're trying to prove ourselves wrong as quickly as possible. Some people have kind of questioned this interhemispheric teleconnection, and this is great because that's how we can make progress. But it seems that something is there, and if, for example, we try to add this new anomaly in our predictive power, instead of correlation here, I'll show you the conditional probability, meaning preserving the joint BDF of ENSO, the Nuno 3.4, and the precipitation, we derive the conditional probability in every year. So if you do a cross-section in every year, you will have the whole probability, not only one expected value. You see, first of all, the explained variance, which is the correlation coefficient squared there, is 9%, not very much. This is after 1980, because I have the reason to include now the Western Pacific connection, the New Zealand index, and see whether it adds predictive ability. Dry success rates, 28%, wet success rate, 30%. Again, if you do a cross-section, this is the whole probability density function. You see it is a little dispersed. It can predict anything. If we add the New Zealand index, we see that the explained variance goes up to 22%. We have some improvement, but not significant, in the dry success rate and the wet success rate. We're investigating now, and it seems like it has more predictive ability for the dry events, meaning the tails of the PDFs. So we have done already better by including one more index in our prediction. But it's the best we can do. And also, well, things change. Should we just pick up indices here and there and define new predictors and put them in a mix? So we're investigating now the whole Pacific dynamics, meaning it's not only the spatial variability, the specific months, but the sequence of this variability in several months that are very important for the prediction of the winter precipitation in the southwestern US. So if winter precipitation is my variable Y, and X is climate predictors, for example, sea surface temperatures, could be geopotential height, or other anomaly, could be salinity that many people started using. In the Pacific Ocean, we can put everything in a regression, but imagine what will happen. For 2x2 grid points in the Western Pacific, you have 22,000 predictors. That's impossible. So we need to be clever in doing a dimensionality reduction that is physically plausible. And here we propose to impose constraints that respect the same time covariance of these climatic variables, which we can learn. So with that, we do a dimensionality reduction, and specifically this covariance would basically tell me that 2 points that are highly correlated should not have very significant different weights as predictors. There is a lot more to say here, but we do regularization. That's called the machine learning. We work with mathematicians at the University of Wisconsin and University of Chicago. So basically, we're going to estimate the weights by both fitting the data, this first term, by doing a dimensionality reduction with the beta. This is L1 regularization that everybody uses, the so-called lasso. But the innovation here is we introduce what we call the graph total variation. That's a methodology that will specifically impose the constraint of the covariance. And as I said before, will give non-dissimilar weights to points in space and time that have strong correlation. Now, the covariance matrix, we can learn it from the data, but it's just one realization. So we propose, and I have here the image, we propose to learn it from climate models where I can have a lot of ensembles and reduce the uncertainty in the estimation of my covariance matrix. Don't forget that the climate models, I can trust the large-scale climatic variables, but I cannot trust the precipitation as a prediction. So how do we do if we do all this machine learning and regularization approaches? So we trained, of course, now machine learning needs training. So we trained in the period of 1940 to 1990. We used, because of the non-stationarity I talked about before, after the 1970s, 80s, we use a non-stationary filter that I don't have time to go through, and we tested it for the period 1991 to 2019, and this is what I saw here. And not only we did that for the total precipitation in the whole southwestern region, that you see at the end of the plot, but we did it for all the climate divisions in Arizona, California, Nevada, Utah that compose the southwest US region. We see that in Arizona we do much better. You see the line, which is the El Nino is the blue. If we add the NZI, the New Zealand index, we do much better in terms of R-square, which is the variance we resolve. And if we use the graph total variation approach, we do even better. These are the red lines. So here, I don't have, but we explain around 40% of the variability in out of sample. This is significant improvement. Don't forget. ENSO alone is 9% of the variance. We added the other index that we proposed was at 22% of the variance. If we can get up to 40% and also do in a way that we reduce the uncertainty and have more confidence in the extremes, that will be very important for water resources and planning. So what's next? Is machine learning the solution? That's the same question I had before. And the same answer, eventually, maybe. But not without testing the causality of the hypothesized mechanisms and the predictors. And we work with climate scientists and atmospheric scientists to perform idealized perturbation experiments, which are specifically designed to understand the process chain of this interhemispheric. If, for example, in a model, I impose this anomaly close to New Zealand, how does it propagate? Do I see it physically for the right reason that it propagates interhemispherically? We also like to differentiate between the Rossby waves versus the Hadley cell-mediated interhemispheric propagation of the anomalies. We also studied the new set of data that came out of the simulations of a MIP6 model outputs, both historical and the future, to understand the time-evolving dynamics that are relevant to prediction. And I put here, because we're doing that now, principal component analysis, but spectral. We look at the phase, what anomalies are propagating where, at what wavelengths. And something that is very important, we don't care to predict the annual amount, but the whole probability density function. That is, what is the likelihood for more than the historical 75th quantile to be materialized next year. If you ask me what we predict for next year, I can tell you that the reception. By the way, I wanted to put a note here. Tomorrow we have a union session, which is on machine learning, innovations for climate and earth surface processes. It's a very carefully selected set of speakers, so if you can do it, it's at 4 p.m. at Moscone South. So I presented some work which I call Beyond the Pixel and Beyond ENSO. We put down some hypotheses, we tested them, and we're still working on both improving in the next generation of operational algorithms for global precipitation estimation, and also to do as much well as we can do in predicting Southwest precipitation, not only, but many other places that are influenced by the Pacific. If I had to give a title again, instead of the boring title I gave in the summer, I would have given Measuring the Unmeasurable and Predicting the Unpredictable. And enough about precipitation patterns. I want to get a little more personal here and talk about patterns of life. When I was 4, my father thought I was smart enough to start me early at school. So he found a way to do that. And this is me next to my classmates in the 1st grade. So I guess I learned how to perform in a room that I was the smallest. At the age of 13, I was asked what I want to become when I grow up, and I said an engineer. So that meant they had to move me from the old girls' high school to the old boys' high school. So I guess I learned how to perform in a room that I was different. I also learned how to dare, and this is a picture that I threw myself in the rail tracks. Yes, I do wear clothes here. And if my kids told me that they did that, I would freak out. But I know they do much worse things, and I'm proud of them, so please keep safe. My group has always been inspiring, and as I said before, we stretch each other and we grow together. They're part of my family. These are pictures going from old times to newer times. They are, for the most part, a happy bunch of people. And the reason I attribute it to what I call positive covariances. I made this slide 10 years ago when we had the NSF Science and Technology Center, and NSF was, in our case, to prove to them that the whole is greater than the sum of the parts. And I said, I can only prove it if I can put it down in equations. So I said, well, if we call x1 the contribution of member 1, or team 1, x2 the contribution of member 2, I cannot possibly expect that the whole will be greater than the sum in the expected value, because expected value is a linear operator, so the expectation of the sum will be the sum of expected values. So nothing to gain. But if you look at the variance, and the variance I explained as the edges, the inventions and all the research that is done at the edges of interdisciplinary, the ideas that have not matured yet, and the collaboration they grow. If I look at the variance is a nonlinear operator, so the variance of the sum is the sum of the variances plus the covariances. Now you can have negative covariance and be in trouble, or you can work on have positive covariances, and then you certainly have the whole greater than the sum of the parts. And in my group, I think we keep our covariances very positive. In the last few years, my group made a Effie bingo for me. I don't tell you what they said Effie stands for. But it has a lot of entries there, some of them that I always pay for their drinks. You know, good luck if you see me not wearing black and all of these things. But I was very proud to see that they listen, because I always tell them the figure captions in your papers have to tell the whole story. so someone can understand. So they put a figure caption here. Incoming PhD students must complete a bingo before a PhD degree may be awarded. Squares with quotation marks indicate precise standalone phrases that must be directed to you. If you're in doubt, it doesn't count. You will know when you hear it. And then the grid was designed to maximize entropy so that each possible bingo has approximately the same probability. So every student in the room that might be interested to do a PhD, they have to be aware of that bingo. So thank you to all my students and postdocs for being part of the extended family, and also my sponsors in all my almost 40 years of career. NSF and NASA have funded my research. The yellow are my current group. Thanks to my collaborators, this is all the people that I have co-authored papers with. This is a lot of people, and I'm proud because I have learned a lot from them. And I leave you with, especially the young people, with something that I stay true to: study hard what interests you the most in the most undisciplined, irreverent, and original manner possible. Thank you.
Thank you, Effie, for a wonderfully scientifically stimulating and also personally stimulating discussion presentation. So we have two microphones, right and left. If you would, please come up. We will take questions for about 10 or 15 minutes, and then we will adjourn. So please make your way to the microphones. We are recording this, so we do want to hear your questions. People are coming.
You showed an increase in R squared by adding New Zealand index and by adding the entire Pacific. But I wonder if it is natural just by adding more parameters in the regression.
Can you speak a little closer to the microphone?
Okay. Yeah, I will repeat my question. So I see there is an increase in R squared after adding the New Zealand index and also adding the entire Pacific. But I wonder if this is a natural phenomenon by just adding more parameters to the regression.
Yeah, no, this is a good point, but you know, if you add more predictors, that does not mean that you're going to do better. And also, you have to see my point of basically, it's not about R squared. It's about really looking at the mechanistic understanding behind these teleconnections. So that the Western Pacific has become a more important factor to consider these days, that's beyond doubt. So if it is only the Northwestern Pacific, or there is an anomaly that originates in the subtropical Pacific, this is something that we are keen to understand for the most important reason that can give you early prediction, which then you can adapt. For example, if I can predict from the anomaly close to New Zealand that starts in late summer, and I can have some guidance for the following winter, updating myself with the new conditions of ENSO and how that anomaly propagates, that's a big advantage. But generally, if you do your job right, and you don't throw things all in there to increase your predictive ability, the chance is that you're going to increase your predictive ability for the right reasons. And I hope I convince you that it's not about throwing everything in, but really exploring the space-time dynamics that have some ability to guide the prediction. I mean, the climate in the Pacific is not irrelevant. We know mechanistically how the anomalies create the Rossby waves and divert the jet stream. So we have to understand what pathways this mechanism can take and incorporate this in a predictive scheme of any sort. I fully sympathize with the question. The more you draw in, the more you reduce the variance, but we're beyond that. I hope I convince you here. So it's a lot more to be done here, and the most important thing, as I mentioned, is to do targeted numerical experiments by which we impose anomalies and see how they propagate and what result they might have on the precipitation in the southwestern US.
Okay, thank you.
My name is Dave Jackson. I'm a seismologist, and I thank the AGU for making it possible for me to hear your wonderful presentation. Really enjoyed it very much.
Thank you very much.
Like you, we in seismology are interested in forecasting and prediction. And like you, we have many different ideas about what are the causes of the things that we can measure. One of the things that we've done that's been exciting over the last several years is to establish a way to do formal prospective tests of ideas about what causes earthquakes. And I wonder if you have in this field any kind of an organization or an organized formal process for not only testing whether forecasts are working, but maybe compare them and try and understand which ones are having advantages over the other ones.
Oh, you know, the community is very large, and we're getting together more and more. For example, the atmospheric sciences community, the atmospheric physics, the dynamicists, the climate scientists, the hydrologists like me, the mathematicians, you know, we're getting together more and more in the last decade for the very important thing that you mentioned, that is compare notes and learn from each other in terms of this predictive ability and what are the most important predictors. I'm optimistic because a lot is happening. Now, of course, different than seismology, we have a lot of development in climate modeling, in the physics of climate modeling, which are, of course, not there. If you have followed the latest trends, is that climate models don't do well. Why? Because they don't resolve the subgrid scale parameterization of the clouds. And we need machine learning to impose this in the models and so forth. So going down to the micrometeorology scale to do better in the large scale dynamics of the climate. So there's a lot to be learned. And I mean, we don't have an organized community, probably as you alluded to in your question. But these connections, including the work that we do with the mathematicians, atmospheric physicists, and climatists, they bring us together in a more systematic way.
Thank you, Effie, for your informative presentation. And I'm trained as a hydrologist, but now I'm entering a meteorology community. And I always found that these two communities talk about the same natural thing in two different language systems. Like we talk about precipitation, we talk about machine learning, estimation, bias correction. But in the meteorology community, they always want to diagnostically resolve different cloud hydromaterials and infer their interaction using kind of more detailed cloud microphysics or even convection parameterization schemes. And when they are using these remote sensing observations, they prefer to try to assimilate, to estimate the cloud status. But in our hydrologic community, we seem to oversimplify this process. I want to know your understanding of where should we go. I know that in that community, they are also trying to combine machine learning for parameterization, but we are going kind of more simplified way.
Yeah.
And what do you think?
So more than 15 years ago, I had done work in my group, actually with Kelvin Drogemeyer, who is now the science advisor to our President Obama. And the question at the time was, can I simulate the microphysics, okay, of a cloud, then run radiative transfer schemes through them, and model the brightness temperature that the sensor would do, so I have more physically based, even databases, and other people have done that. Guess what? We know the physics, but at the same time, the resolution at which we can run the model at the microphysics level is a lot of uncertainty. And that's why even NASA, for the operational algorithm, well, in fact, they started with physically computed databases. That is, I impose different cloud structures, run my additive transfer, and I form a database which is physically informed. They gave up on that, and they use the radar observations coincident with the microwave because they're more faithful to what really happens. So this might not answer directly your question, but I see your point. I mean, there is the going down to understanding the hydrometer level interactions and so forth, which is very important, as you know, for weather prediction, even now for climate, versus an approach that looks, at the bigger picture. Can I use what climate models give me and what large-scale observations give me to do a better prediction of hydrometeorological variables? So I will go back to my answer to the previous question, that is, there's a lot to be learned among the communities. I put there cautiously, I have done machine learning. We didn't call it machine learning years ago, but I've done all of the above, starting with regularization and so things with my former student, Ardeshir Ebtehaj. And I am very cautious about, first of all, giving our problems to the computer scientists. We have to be behind checking the physics for all of the more advanced mathematics that we do for prediction. So it's an interdisciplinary field that atmospheric scientists, hydrologists, and mathematicians have to work together, and I hope we do that in the community.
Okay, thank you.
Thank you. Well, I'll ask one question, which is relates back to the shift in the weather patterns from pre-1970 to post-1970. Do you care to speculate on what the physical mechanism was in the Western Pacific that led to that significant shift?
No, I'm not. I'm not ready to speculate. But I welcome other people to speculate and test it. And we hope to do some of that, again, with the numerical, idealized, targeted experiments. But the only thing we can tell now, and I hope I went quickly through that, is that we cannot reject the hypothesis that there is external forcing as opposed to only internal variability that is responsible for these patterns. And this is the reason also, as I witnessed with many new publications, that they look at the Western Pacific more and more as the cause. And of course, there are many things that I cannot cite now, but there are climate people that are looking at this very rigorously and actively right now.
Okay. Well, please then, thank you, Effie. If you will, please join me in thanking Dr. Fafula Georgia for outstanding work.
Thank you.